What's good, math family? In today's video, we're going to look at the easiest method to simplify radical expressions, whether those radicals have numbers or variables and exponents. When we simplify radicals, family, a lot of times students may forget their perfect squares, and it happens. But with this method, no matter the factors you use, you will get the correct answer. So in a perfect world, we know that square root of 36 is just 6. This should be our answer. But if for some reason you just forget, another way to do this is just use a prime factorization tree. So we could break 36 down. Let's say we did 18 times 2. So right now we know that 2 is a prime number. We cannot divide it by anything but 1 in itself. So now we focus on 18, and we're going to break this down as 9 times 2. Now, when we look at this, we have one pair. And this is important because we're talking about square roots. So every pair that we have, we're going to pull that number out. But before we get there, we have to break down 9 as 3 times 3. So now what we want to do is focus at the end of the tree. So here and right here. And every time we have a pair, we're just going to pull this out. So this is going to be 3. This is going to be 2. And once we simplify by multiplying, we are going to get the same answer of 6. And if you think about it another way, this is just 9. The square root is 3, right? 3 times 3 is 9. Square root is 3. This is how we get the answer. Now let's say we didn't use those factors. Let's say for 36, we used 9 times 4. So right here, we would break this down as 3 times 3 times 2 times 2. And when we look, we'll get the same exact thing. We have a pair of 3's here, so this comes out as 3. And this pair of 2 comes out as 2. And once we simplify by multiplying, we're going to get the same answer of 6. This is why this method is so perfect. Now, in example number 2, let's say we didn't go straight to radical 4 times radical 6, and we simplify our perfect square to get 2 radical 6. If we use the same method of a prime factorization tree, we could use these two factors, 12 times 2. Right here, we notice that we can't break down 2 anymore, so we're going to focus on 12. We break down 12 as 4 times 3. We know 3 is a prime number, so we're going to focus on this 4, which will break down to 2 times 2. So we have a pair here, right, which we could pull out as 2, and then what's left over? We're not paying attention to 4 because we broke that down. We're paying attention to the end, those end branches. So we have this 2 right here from these two, and then we have this 2 and this 3. So once we multiply that together, it's going to stay under the radical as 2 radical 6. So in the third example now, we're breaking down radical 20. And radical 20, let's say we did 10 times 2. We know 2 is prime, so we're going to focus on 10. And when we break 10 down, this is going to turn into 5 times 2. Now at this step, all of these numbers are prime. Only could divide them by 1 in itself. So I have a pair of 2's. That comes out as just itself, 2. And then this last 5 right here is going to stay under the radical. And if you want to double check to see if this is right, all you have to do is square this outside number. 2 times 2 is 4. When we multiply that by 5, we're going to get the same radical 20 as an answer. Now, if we did it another way, right? Let's say we use different numbers. Let's say we used 4 times 5. We used the perfect square. 5 is prime, and when we break down 4, we're going to get 2 times 2. And when we look at these numbers, we know that we could pull out that 2, and our prime number of 5 is going to stay under the radical. This is why this method is so key, and now we're going to go on to more examples. Now we're going to focus on simplifying radicals with variables and exponents. So if we follow that same method, we could break 48 down as 8 times 6. And then we could just write our variables out. So we have x to the third times y squared times z. So now at this step, we could break down 8 as 4 times 2, and then we're going to break down 4 as 2 times 2. So we know we have one pair here, have a prime 2 right there, and then when we break down 6, this is going to turn into 2 times 3. So right now, this is what we have. We have one pair of 2, so this comes out the radical. Our second pair comes out as well. And then now, under the radical, we know we have that 3. Now when we focus on the variables, the same thing applies. So we have 2 x's, this comes out as x. That third one, because we don't have a pair, it stays under the radical. We have y times y, we pull that out as y. And then the same thing with z. Because it's just 1, we don't have a pair, it stays under the radical. Now when we simplify this on the outside, this is going to turn into, go right here, 4xy times radical 3xz. And that would be our final answer. In a perfect world, let's say you went straight to your perfect your square roots, your perfect square roots. You could have done this. You could have had 16 times 3 times x to the third y squared z. And when we do it like this, just remember we could divide our exponents by 2 since we're dealing with square roots. So 4 is going to turn it to its square root, which is 4. 16 is going to turn to its square root, which is 4. 3 stays under the radical. X to the third, we could pull out 1x. So that comes out. We have 1 left under the radical. Y squared comes out as y, right? So that's everything we could pull out. And then, like we said, under the radical, we have 3. That last x, that will give us x to the third. And then that z, that is by itself. As we move into this last example, if this video has been helpful, just smash the like button for us. Really helps our channel to get this out to more students. So we're talking about 12x squared y to the fourth. So if I use that prime factorization tree, let's say I did 6 times 2 instead of using 4 times 3, right? Then we have x times x, and then we write our y to the fourth. So right here, we know that this 2 is prime. We can't break it down anymore. So we focus on 6, and now this turns into 3 times 2. So right here, we notice that we have one pair. So that 2 is going to come from out under the radical, right? Then we notice we have a pair of x's right here. So this comes out as x. We have a pair of y's that come out as y. And then our last 2 y's are also going to come out. So now the only thing that is left under that radical is just 3. And when we simplify the expression even further, we're going to have 2xy squared times radical 3. And this is how you could solve radicals even without knowing your perfect squares 100%. We really hope this video was helpful for you, math family. If it was, smash the like button for us, subscribe to the channel, and leave comments down below if you had questions on this video or if there's videos you want to see on our channel in the future. Thank you guys so much for watching Algebra 1 with Mr. Peters.